So here we are with electricity generation and consumption. And the first thing I want to mention or get into is the fact that, as you know, electricity can't be mined or captured anywhere on Earth. If you think about coal mines or wind turbines or photovoltaic cells or biomass plants, in none of these cases is electricity actually grabbed from somewhere. It's always generated. Because the natural environment, short of lightning, doesn't produce any electricity that we can actually acquire. So we have to generate electricity in order to power our lives. And in order to do that, we need something called a generator. Now, a generator can be many different designs, from very small scale, what you buy, say, in a local hardware store for emergencies, to large scale generators for utility scale power plants. And these can occupy many square meters of space, be large as say a couple school buses. The core of every generator, though, basically has two very important components, and that is magnets, and sometimes these are permanent magnets, and sometimes they're electromagnets. In either case, all generators have magnets, and then also all generators have copper coils, and these copper coils then spin in relation to the magnets, and the spin is as very close together as possible. And we'll explain why that is in the next slide when we look at a simplified model of a generator. But you always have to have magnets, and you also always have to have copper coils in order to have electricity being generated, at least in this respect. So in many cases throughout the world, we of course use non-renewable energy resources to generate electricity. And in this example here, we're using, say, coal as an example, because that's the most common energy resource that's used in order to generate electricity. So we have the standard procedure for generating electricity with coal, in that you acquire coal from a coal mine, you crush it, you then route this crushed coal into a large furnace. The furnace is where it's burned. It's lit, usually with natural gas burners, and an enormous, basically, kettle is created where fire and flames rise maybe 2 or 3 stories high, and they pass, and in this kettle you have pipes that contain water. And in these pipes then the water is routed, and these flames then of course heat the pipes then heat the water, and the water then changes state. It changes from a liquid into a vapor, and in that manner acquires a lot of the energy from the burning fuel. The steam then is routed to what's called a steam turbine. The turbine doesn't do the electricity generation. All the turbine's job is to spin. That's the only thing it's supposed to do. And these turbines then spin very fast, sometimes Mach 1 or 2 or even 3 times the speed of sound, in order to generate electricity via a spinning shaft. So all these steam turbines then have a shaft in them, and that shaft is connected to what actually does the electricity generation, and that's the generator. So the turbine shaft spins a generator, and then the generator actually generates electricity. So that would be an example of a non-renewable resource, such as coal, being used to generate electricity. An example of a renewable energy resource that can be used to generate electricity is, say, with wind. So we have a wind turbine. Wind blows through the turbine spins, and that then turbine has a shaft, and that turbine's shaft then spins the generator, and then electricity is generated from that. So it's a much simpler process in this case to the coal example that we just mentioned. Now in this slide we see a very simplified generator. Notice that there are several components here. First, the outside housing of this generator is very dense steel and steel alloy. That's because it's got to withstand a lot of torque, a lot of strain from these spinning components. Notice in the center we've got a rotating shaft, and on that shaft, at least in this model, you've got copper coils. So these coils are made of basically copper wire. Copper is a very good material to generate electricity with. So you have then copper coils, and these are just basically loops of copper. And notice then around the perimeter of this generator, you've got a series of magnets. In this case, you could assume that these magnets are permanent magnets, and these permanent magnets are the same kind of magnets that you've picked up and stuck on your refrigerator, you could say. In this case, we're probably using neodymium magnets, that is rare earth magnets, so they're extra powerful. So the shaft from the steam turbine and or the shaft from the wind turbine will be connected to the rotating shaft here in this picture. And as that then spins, the copper coils spin in relation to the magnets. And notice in this picture that the magnets and the copper coils are held in very close proximity. The reason is that we want the copper coils to pass as close to and as close within the magnetic flux lines of the magnets. The more magnetic flux and the more copper coils come close together, the more electricity, the more electric current is generated. So we get a lot more current if we have the copper coils located in very close proximity to the magnets. And depending on how fast the shaft spins, we get more or less push of the electricity through the wires, and that's called voltage. So a small spin, a slow spin, would generate a lower voltage than a very fast spin. The faster you spin it, the more voltage you get. So in this model, we've got then the copper coil situated in the center while the magnets are around the perimeter. This is not the only way a generator can be designed, though. You could also have the magnets be on the inside while the copper coils are the things on the outside, and have the magnets do the spinning rather than the copper coils. This kind of design is what you would commonly see in commercial scale wind turbines, where the magnets do the spinning and the copper coils are static or fixed.